In section 7.1, we're going to look at the standard normal distribution. And the normal distribution is pretty much the foundation for what we're going to do in the rest of the course, which is making confidence intervals and testing hypotheses. And so we're going to look at this pretty extensively. And this is also the first time that we're going to be using a statistical chart or a statistical table. And there is a link to the tables on this module in Canvas. So if you look right above where this video is posted, there should be a link to the tables. You also should have them in your textbook. But if you just want to print out a copy to have handy. But either way, you want to have those tables in front of you. It's 3 pages. We're going to use 2 of the pages today. You want to have those tables in front of you as you watch this video, because I'm going to teach you how to use them. Okay, so the standard normal curve is based on z-scores, and this refers to the same z-score that we talked about back in chapter 3. Remember, the z-score is equal to the data value minus the mean divided by the standard deviation, and it's the number of standard deviations away from the mean. So it might be above the mean, it might be below the mean, but it's the number of standard deviations you are from the mean. And we learned in, I believe it was chapter 3 as well, about the empirical rule, that when you have a bell-shaped distribution, like the standard normal distribution is, that's what I have drawn here, we know that roughly 68% are within 1 standard deviations, 68% of the data. 95% roughly are within 2 standard deviations, and almost all is between 3 standard deviations. Well, we're going to look at this more exactly now. Instead of the empirical rule, which is just an approximation, we're going to be able to get these areas and probabilities exactly. I also want to mention that this is the first distribution that we're looking at that's continuous. So we're no longer talking about discrete. We're talking now about continuous distributions. And with the standard normal distribution, like I said, it's bell-shaped and symmetric. These are z values that are down along the horizontal axis. And so once you standardize it and make it the standard normal distribution, the mean is going to be 0 and the standard deviation is going to be 1. So the mean's going to be right here at 0, and then we'll just go, it's just like the number line. Let me go ahead and just make that 0 actually. And then it's just like the number line. So we've got 1, 2, and we know that almost all of the areas between -3 and +3. So we have -1, -2, and -3. Like this. So this is like the number line, with 0 being at the highest point under the curve. And what we're going to be interested in finding are the areas under the curve. So if any of you have had any calculus, the definition of the z-curve actually is an integral, because the integral is the area under the curve. Just little FYI. Don't need any calculus for this. For the theory you do, but we're not going to go into the theory. And so because this is symmetric, 50% of your area is going to be on this side, and 50% of your area is going to be on this side. And the total area under the curve is equal to 1. And I purposely drew this so that the curve itself is not touching the z-axis. That's how it is. It kind of just goes along. It gets closer and closer to that z-axis, but it never actually reaches 0. And what we're going to do is we're going to use a table, and I'll show you how to do that, to compute areas under the standard normal curve. Now the reason we want to compute areas is because an area, when you calculate that area, it's equivalent to finding the probability. So, for example, if we wanted to find the area to the left of 0, well, we know that that's 50% because that's right where the standard normal curve is split in half. Screen's acting weird. It's going to be 50%, but that's equivalent to finding the probability that your z-value is less than 0. And so that area is the same thing as the probability, that area to the left. And another thing I want to mention is because this is now a continuous distribution, we don't care at all if you put an equal to or don't put an equal to. If I put an equal to there, it's still going to be 0.5. We had to be so careful about the equal to's with the discrete distributions. With the normal distribution or any continuous distribution, we don't even worry about that anymore. Okay, so the first thing I want to do is show you how to use the table. So we're going to look at some examples. Really, that's all we're going to do in this section is practice using the table. So for number 1, they want us to find the area under the standard normal curve to the left of z equal 0.94. Now, I want you to draw a picture of the standard normal curve every time you're finding an area. It's going to help you avoid mistakes. So we know that 0 is right here. So think about on the number line, where would 0.94 be? Well, it's going to be to the right of 0. I don't know where exactly. You don't have to be that exact, but it's going to be roughly about right here. And we're trying to find the area to the left. So we're going to shade this way. So it's this area right here that I'm trying to find. This is equivalent to finding the probability that z is less than, because it's to the left, 0.94. That's equivalent. So we can get that from the table. So I'm going to bring the table up and I'm going to show you how to use the table now. So if you printed it out or if you look in your textbook, the table we're interested in is A.2. Whoops, I have it on highlight. Hold on, because I want to be able to highlight. Let's delete that. Okay, let me take the highlight off so I can scroll. So we have table A.2 is on 2 pages. And then the third page, if you printed it out, is table A.3, which we're going to learn about in chapter 8. So we're just going to concentrate on the first 2 pages. And so notice that in your the table, what the table is giving you is you're going to find the z-value. Let me switch to highlight. You're going to find this z-value. Maybe it won't let me. And then once you have that z-value, then the number in the table is giving you this area to the left. So the table gives us the areas to the left. So for this one, we're going to look at 0.94. So we want the area to the left of 0.94. The first page of your z table has negative z values. So I'm going to see how we have negative 3.6, negative 2.5. I'm going to scroll down to the second page, which also still gives us the areas to the left. And the first column is going to be the ones and tenths place of your z-value. And then the top row gives you the hundredths place. So for 0.94, we're going to go down to 0.9, which is right here. Let me highlight that. And then we're going to go over to 0.04. Let me highlight that. And so where they intersect, that's the value you're looking for. And that is automatically the area to the left. So the area to the left is 0.8264, and that's equivalent to this probability. So if you were to randomly select a z-score, the probability that it's less than 0.94 is about 83%. Equivalently, the area, the proportion of the curve that's shaded in my picture is about 83% of the area. Okay, let's do another one. And again, we're still doing it as to the left. It's going to be different when we do to the right or various variations on that. But when it's to the left, that's just the value that's in your table. So here we're looking at to the left of negative 2.37. So I'm going to draw my standard normal curve. Here's the mean at 0. So negative 2.37 is going to be to the left of 0. And it's going to be pretty far over there because we know that negative 3 to positive 3 is most of it. So negative 2.37 is right here. And again, we're looking for the area to the left. So we're looking for this area right here is what we're going to find. And when we find that area, it's equivalent to the probability that z is less than or equal to negative 2.37. And I purposely put an equal to on there just to remind you that it doesn't matter. We do it the same way. So I'm going to go back to my standard normal curve. Let me delete what I did here. And we're looking at negative 2.37. So I need to go back to the first page, which is where the negative z-scores are. And in the first column, we're going to go down to negative 2.3, which is right here. And then the hundredths place is 0.07 because it's negative 2.37. So this will be our hundredths place. Whoops, went crooked there. So where they overlap is that area. So it's 0.0089. Now, the reason for drawing the picture is kind of twofold. One is it can kind of help you see that your answer makes sense. If you look at this one where we drew the picture, it's going to make sense that we have a very small area, which we do. It's less than 1%. If you look at the first one, 50% occurs at 0, so I know I'm going to get an answer bigger than 50%, which I did. Another reason you want to draw the picture is for when we do this later, the visual is really going to help you plug this into your calculator because we're not always going to use the table. But I think it's important to know how to use the table. So for this section, you're going to be using the table. Okay, let's look at another problem now. Now for this one, we want to find the area under the standard normal curve to the right of some values. So if we look at the picture, here's our standard normal curve with the mean at 0. Negative 1.09, that's going to be to the left of 0 because it's negative. 1 is about right here. It's kind of where the graph goes from where it's concave up, where it would hold liquid, to where it switches to concave down. Kind of another calculus term there if you've had it. But that's roughly where 1 is. So negative 1.09 is not going to be much off of that. But this time we're looking to the right. So we're going to shade this way. Okay. Now the table, remember, will always give us the area to the left. So when we look this number up in the table, we're going to get this unshaded area. So think to yourself, how would we do this? How would we, if the table's going to give us what's unshaded, how can we get what's shaded? Well, hopefully you're thinking of the complement. The total area is 1. So if I subtract what I'm given from the table from 1, that should leave me with the shaded area. So when you're doing an area to the right, it's a greater than. We're finding the probability that z is greater than negative 1.09. That's equivalent to doing 1 minus the probability that z is less than negative 1.09. because this number right here is what the table gives us. The table always gives the area to the left. So if you want an area to the right, you're going to subtract the table value from 1. So this will be 1 minus, and now let's get that table value. Okay, so we're still on the negative page. It's negative 1.0. So we're going to look at this row. 9. So 9 is the last column. So we're going to look at this column. And so we can see the value is the one that's where they match up. It's 0.1379. So we have 1 minus 0.1379. And if you subtract that, you're going to get 0.8621. So that yellow shaded area is 0.8621. And again, does it make sense that it's bigger than half? Yeah, because we've got more than, 50% is from 0 up. We've got more than that over here. Now, I do want to show you something real quick. Because of the symmetry, another way that we could have gotten this answer is we could have looked at positive 1.09. Let me show you how that works. If you look at 1.0, I scrolled past it, and then over to 0.09, you don't have to subtract it from 1. Notice that we just have our answer, that 0.8621. So that's another way to do it, and that's just because of the symmetry. So if you found the area, to the left of positive 1.09, that would be this area here. That's equivalent to that yellow area. I usually still just do it with the 1 minus. Okay, let's do one more that's to the right. So this time we're looking at to the right of z equal 0.47. So I'll draw my standard normal curve. Here's 0. So if you think about where 0.47 is, it's going to be on the right of 0, but very, very close to 0. This answer is probably, it's going to be less than 50%, but not by a whole lot, 10% or so. And then we're looking to the right. So this is the area that we're going to find. And so finding this area is equivalent to finding the probability that z is greater than 0.47. And with the greater thans, we're going to do a 1 minus the probability that z is less than 0.47. And that is the value you get from the table. So if I go to the table, so for 0.47, we're going to start with 0.4 right here, and then go over to 0.07 right here. And so you can see we get 0.6808. So we have 0.6808. And so when you subtract that from 1, we get 0.3192. So that's about 30% of the area, total area, that is shaded. Okay, so that's how you do them when they're to the right. Next, we're going to look at how do we find the area when it's between two values. So let's look at that next. So for this one, we want to find the area under the standard normal curve that lies between z equal negative 1.28 and z equal positive 1.36. So let's draw a picture. Here's our mean at 0. Negative 1.28 is right here, roughly. And 1.36 is right here, roughly. And we're finding the area in between those two values. So how we write that as a probability is we're finding the probability that z is greater than negative 1.28 and at the same time less than 1.36. Okay. So let's calculate this. So first of all, when you look these numbers up in the table, let's think about what you're finding. It's always, the table always gives you the area to the left. So if we look up 1.36 in the table, it's going to give me this entire area, even what's not shaded. Now, if I look up negative 1.28, it's going to give me this area to the left. So think about how we can get what we want, which is what's shaded in yellow. Well, if we find the larger area and then subtract away the smaller area, it's going to leave us with just the shaded area. So what we're going to do is we're going to find the probability that z is less than the larger number minus the probability that z is less than the smaller number. And we'll get that difference, and that will leave us with the area that's left in the middle. Okay, so let's find those two values on the table. Okay, so the first one that we want to find is less than 1.36. So I'm going to go down to 1.3, which is right here, and then over to 0.06, which is right here. And where they meet, that's your value. So it's 0.9131. Okay, minus, now we are going to do the same thing for negative 1.28. So for the negative values, get rid of these. Okay, so we're going to start with negative 1.2. Which is right here. And then we're going to go over to 0.08, which is this one. I kind of lost I didn't go straight there. But the you can see that where they meet is right there at 0.1003 is what you should get. And so you're just going to find that difference to get the shaded area. And that leaves us with 0.8128. So remember, when you find that area, it's equivalent to finding a probability. So if we were to randomly pick a z-score, the probability that it falls between negative 1.28 and positive 1.36 is about 81% probability. Let's do another one of those. Okay, so for this one, we're looking at z between negative 2.10 and z 0.017. Z equal 0.017. So let's draw the picture. Here's our mean at 0. Negative 2.10 is going to be roughly over here. And 0.07 is going to be really close to 0, but on the right side. I'm not putting a lot of effort into placing them. I just need a quick visual. Don't make a big deal out of it. Oh, there go my dogs. Okay. So this is the area we're trying to find. So just as a little reminder, when we look up the larger number in the table, that's going to give us this entire area. When we look up the smaller number, it's going to give us the unshaded area to the left. So we need their difference to be left only with the shaded. So we're finding the probability that z is greater than negative 1.0 and less than 0.07. And to do that, we do the probability that z is less than 0.07, the number on the right, minus the probability that z is less than negative 2.10, the number on the left. Okay, so for positive 0.07. Let's calculate that. Okay, so we're going to go to 0.00 and then 0.07. So right here, and so that number we're looking for is 0.5279. Minus, now we're going to do the same thing for negative 2.10. So for negative values, you're going to use the first page, and it's negative 2.1, which is right here. And then the hundredths place is 0, so that's your first column. And so we get 0.0179. And so if you do that subtraction, we get 0.5100. So 51% of the area is between those two values. Okay, one last scenario for using the table is when we're looking at finding the area in two tails of the standard normal curve. This is saying find the area under the standard normal curve that lies, that should be an S, that lies outside the interval between these two numbers. So what this is saying is, let's look at it visually. Here's the mean at 0. Negative 1.11 is going to be roughly about right here. And 3.21 is going to be roughly about right here. It's way out there. So what they're asking us to find is the area that lies outside that interval. So we want this tail and this tail. So we're finding the area in the two tails. So we're finding the probability that z is less than negative 1.11 or z is greater than 3.21. That's what we're finding. It's an or probability. So we're going to add them together. So we're just going to calculate each of them. So the first one, that's easy. It's to the left. You're just going to find that number in the table. Plus, for the second one, remember that to do an area to the right, we're going to do a 1 minus. So this will be 1 minus the probability that z is less than 3.21. Okay, so let's get these numbers from the table. Negative 1.11. Well, we're going to go to negative 1.1, which is right here. And then it's 0.01, so that's your second column. So it's right here. So it's 0.1335. Plus 1 minus, and now to the left of 0.312. So I need to go to the positive values. So 0.31 is way down here. And then it's 2. So this is 0, 1, 2. But you can't see the whole thing on my computer screen. And so we get 0.991. I think I'm looking at the wrong thing. Hold on. It was 321. Wrong thing. Hold on. This one's wrong. 0.32. There we go. And it's 0.321. They're both wrong. I switched them up. There we go. And so we get 0.9993. And so if you do that arithmetic right there, you're going to end up with 0.1342. So that's the combined area in those two tails. Let's do another one of those. Okay, so here we're looking at, in the tails, the area outside of z equal negative 2.73 and z equal negative 1.39. So we have the mean here at 0. Negative 2.73 is going to be roughly about right here. And negative 1.39 will be roughly about right here. Oh, no, it's negative. Wrong place. Negative 1.39 is going to be roughly about right here. And so then we're looking for the area in these two tails. By the way, an alternate way to do this problem is to find the area in between the two numbers and just subtract it from 1. You can do it that way too. I think it's equal amount of work, so it doesn't matter. So we're looking for the probability that z is less than negative 2.73 or z is greater than negative 1.39. So that will be the probability that z is less than negative 2.73 plus 1 minus the probability that z is less than negative 1.39. Okay, so let's find those values on our table. So negative 2.73, I need to go to the negative values. Okay, so negative 2.7 is right here. And then we're going to go over to 0.03, which is right here. So we get 0.0032. Plus 1 minus, now we're going to look at to the left of negative 1.39. So negative 1.3 is right here. And then 0.09 would be the last column right here. And so that's 0.0823. And so if you do that arithmetic, you should end up with 0.9209. And so that's the area that's shaded in this picture. Okay, so that's how we find probabilities in areas using the standard normal curve. Now, sometimes we want to do the reverse. And that's what I want to talk about next. What if we know the area and we want the corresponding z-score? So like, for example, what if we have this scenario? Where we have like some value, z, and we know that this area, let's see, it's going to be a pretty large area. Let's say that we know that it's equal to let's just say 0.83. And the question is, if we know that area, what z-score gives us that area? So sometimes we want to do it in reverse. Well, how we used to have to do it is we would go to the table. So first you would have to decide, okay, is this z-score going to be positive or negative? Well, since the area to the left is 83%, 50% would happen at 0. It's bigger than 50%, so it's going to have to be a positive z-score. Another reason why the picture is helpful to draw. So I should get a positive z-score. So what I would have to do before we had these calculators is I would have to go to the positive z-scores. Let me delete my highlighting. And you would look in the meat of the table. So we're not looking in the first column and the first row. You're looking at all these values inside the table, and you want to find the one that's closest to, what did I say, 0.83? Yeah, so we want to find the one that's closest to 0.83. So we've got a couple contenders right here. We've got 0.8289, which would round to 0.83. And we've got 0.8315, which would also round to 0.83. So what you would have to do is, we called it extrapolating, you would have to decide which one is closer to 0.83. The 0.8289 is 11 units away. The 0.8315 is 15 units away. So we would pick this one, the 0.8283, and then you would look at what z-score that is. So it's 0.95. So I'm going back and looking at what values right here, 0.95, that's what gives us that z-score, or that area. So the z would have to be 0.95. Now, luckily, we don't have to do it that way. This is something that we can find on the calculator. And how you do it, and that's the best way to do it, is with the calculator, is we're going to use something called the inverse normal. And so to get that, you go into that VARS menu that we were using for the binomial distributions. So you're going to go into second VARS, which takes us into the distributions. And you're going to select number 3, which is the inverse normal. It's inverse normal because normally we're looking for the area and we know the z-score. Now we know the area and we're looking for the z-score. So we're doing the reverse. And so to get that z-score, you're going to use the inverse normal, and you're going to enter 3 numbers. And the 3 numbers that you enter are the area to the left. It has to be to the left. That's important. The mean and the standard deviation. Now, for the standard normal distribution, the mean is 0 and the standard deviation is 1. But we're going to talk in the next section about distributions that aren't standard normal. So this will work for any mean, any standard deviation, as long as you have the normal curve. But for these, it's going to be 0 and 1. So let's redo this problem using the calculator. We should get the same number. Okay, so z is going to be the inverse normal. The area to the left is 0.83. The standard deviation is 0, or the mean is 0 and the standard deviation is 1. And we'll do that on our graphing calculator. So we'll go to second VARS. Number 3 is your inverse normal. The area to the left is 0.83. The mean is 0 and the standard deviation is 1. And we always round z-scores to 2 decimal places, so we get that 0.95 that we found in the table. It's much easier to do it on the calculator, and that's how I'm going to do these examples now. We'll use the calculator. Okay, so for the first one, we want to find the z-score for which the area to its left is 0.13. So let's draw our picture. Mean at 0. So if the area to the left is 0.13, we know the area to the left of 0 is 50%. 13% is smaller than 50%. So my z-score is going to have to be on the left over here. It's going to be negative. And then this area right here, because we're looking at the area to the left, we know that to be 0.13. Whoops, So this is going to be 0.13. So whenever you know the area and you're looking for a number on the number line, that's when you use the inverse normal. So z is going to equal the inverse normal. And just like when we were doing the binomial, you should write down what you're typing in your calculator. It's really the only way to show some work. You always use the area to the left, so that was what was given to us, 0.13. The mean is 0 and the standard deviation is 1. And so that z-score is second vars number 3. So we have 0.13, 0, and 1. And so that area, or that z-score, is negative 1.13. So here again, this illustrates why drawing the picture is important. We knew that we were expecting a negative z-score because the area has to be to the left. So if I'd gotten a positive number, that would have told me that I did something wrong. Okay, let's do another one. Find the z-score for which the area to its right, so this is different than the last one, is 0.09. Okay, so let's draw our standard normal curve. Here's the mean at 0. And we want the area to the right to be 0.09 or 9%. So think about where your z-score is going to be. If the area to the right is smaller than 50%, my z-score must be over here on the positive side, because the area to the right, this area right here, is 0.09. Okay, so to calculate that z-score, we're going to use the inverse normal. But a common mistake that I want you to avoid is this number right here, whatever we plug in here, this must be to the left. So even if they give you an area to the right, you've got to switch it around so that it's to the left. So if 9% is to the right, then we're going to have 91% or 0.91 over here on the left. This whole thing is 0.91. So I've got to use that value for the area to the left. So that's going to be 0.91. And then the mean is 0 and the standard deviation is 1. And that should give us a positive z-score. So second vars number 3. So we said the area to the left was 0.91, and then we have 0 and 1. And so that gives us 1.34. You always round your z-scores to 2 decimal places. And that's just because that's the conventional way. That's how it was done when the tables were created. Okay, let's look at another one here. This is the last one. Then I have some notation things to talk about. So for this one, they want us to find the z-scores that bound the middle 70% of the area under the standard normal curve. So what they're saying here, again, it's always helpful to look at a picture. Here's 0, the mean. We want to find 2 z-scores. We're going to have one on the negative side. We'll call that one z1. And one on the positive side, we'll call that one z2. So that this area between them is 70% of the area. So that area inside of there is 0.7. Okay, So to calculate, let's calculate Z1 first. To calculate Z1, we're going to do the inverse normal because we know the area. We're looking for the Z value of, now right here I'm going to need the area to the left. Well, look over here at our picture. If we have 70% in the middle, that leaves 30% that's not accounted for, that's not being shaded. Because of the symmetry, it's going to be split evenly. So 15% will be here, or 0.15, and 15% will be here, 0.15. So the area to the left of Z1 is 0.15. And then the mean is 0 and the standard deviation is 1. So for Z1, we have 0.15 and then 0 and then 1. And that gives us, going to 2 decimal places, negative 1.04. Okay, now for Z2, I'm going to show you 2 ways to get it. To calculate it directly, because when we get to things where if 0 is not right in the middle, things don't work out so pretty. So I'm going to show you how to do it that'll work anytime, even when we're not at the standard normal. So to get Z2, I need the area to the left. Now the area to the left is the whole thing, all the way down. So it's going to be that 0.7, but it's also going to be the 0.15. So the area to the left for Z2 is 0.85. And then the mean is 0 and the standard deviation is 1. But because it's all centered around 0, you're going to get the same number that you got for Z1. It's just going to be positive. That's because of the symmetry. But I'll go ahead and show you. So we have 0.85 and then 0 and 1. And that gives us positive 1.04. Now, in real life, this is what the bounds that cut off that 70%. In real life, we don't always have a mean of 0. You can have all sorts of different means. And so it's not necessarily just going to be a change in sign if it's not centered around 0. So that's why I wanted to show you how to work it out. Okay, the last thing we have to talk about is a notation thing. It's not really a new calculation. We're still going to do the calculation the same way. But this notation, this letter right here is the Greek letter. It looks kind of like the Christian fish symbol almost. But it's the Greek letter alpha. It's like A in the Greek alphabet. And so when you have Z sub alpha, the understood meaning of this notation is it's the Z-score with an area of alpha to its right. Let's do it this way. With an area of 1 minus alpha, let's do it that way, to its left. So like, for example, if you're trying to find Z sub 0.025, so in this case, my alpha is 0.025. So 1 minus alpha will be, I think, 0.875. I don't trust my decimals in my head right now yet. Oh, 0.97. Good thing I checked it. 0.975. So what this means is this is the area to the left. So visually, what we're looking for is on the standard normal curve, we're looking for the z-score that has 0.975 area to its left. So we want this z-score so that this area to the left is 0.975. And so that's just our inverse normal key. That's what we want, the area to the left. So z sub 0.025 will be the inverse normal of 0.975 and then 0 and 1. This is a notation that we're going to use later when we get to confidence intervals and hypothesis testing. So to find that value, we'll do second bars number 3, 0.975, and then 0, and then 1. And so that z-score is 1.96. All right, and that finishes up. I think that was my last. Yep, that's it. That finishes up this section. So in the next section, we'll be applying these normal distributions to real life situations, and we'll learn how to calculate these probabilities and areas on the calculator as well.